Welcome to a read along with Dr. Pal in the book Discrete Perspectives in Mathematics. We're currently looking at example 4 in subsection 3.2.2. Okay, so sometimes our committees are made up of different things, um, like X moves, Y moves, Z moves, but they can also be made up of people wearing shirts of different colors. Okay, so like for instance, if we take a look here, um, maybe we're trying to form a committee of different people, and these are options that are coming from a particular committee um, that we're trying to pull from. Maybe we want two people with a blue shirt, or one person with a blue shirt, or maybe we'll just take one person with a red shirt coming from a particular committee, or no one at all, in order to make a new one. Okay, so let's see. So let's suppose this is a committee, and let's suppose we found another committee with different options. All right, maybe this means one person with red. So that maybe this means two people together, one with red and one with blue. And we're saying maybe there's two different ways of doing that. One way of doing this, one way of doing that, one way of doing that. Um, okay, so maybe these are our different committees of what we can do. So maybe we want to form a new committee that have two people with blue shirts and one with a red shirt. So that means we're looking for the coefficient of b squared r cubed. So this example just shows you that we don't just have to use x's per se, but we could do other things as well and have different kind of things interplaying. So one committee could have these as its options. All right. So one way of doing one red, one way of doing one blue, two ways of doing red, blue, and so forth. So we can multiply these together, and we get that the coefficient is 3 right here. So there's 3 ways of forming that committee. So that's just another way of looking at it. Okay, so maybe we don't care about shirt color anymore. Let's look at another example again. Or let's kind of go back to just X's again. So let's suppose that we want to choose a committee C with 5 people, and we want to start with committee A with 3 and committee B with 4, with no restrictions at all. Let's think about what that would be. So, first of all, what are our committees, right? So we have committee A and B. Okay, so we just have committee A times committee B. What is committee A now? Well, if we look at it right here, there's no restrictions. So we could either choose 3 people from it, or 2 people, or 1 person, or 0 people from this committee of it's of 3 people, right? Well, how many ways they were choosing three people from 3 things? 3 choose 3. Hey, that's a binomial coefficient. 3 choose 2, 3 choose 1. Our frequencies are just binomial coefficients. Now, if you notice, these binomial coefficients put together actually make this polynomial right here because of the way they were designed, right? This is the coefficient of this for the constant term, coefficient for that. So it's basically what we're saying is 1 plus x cubed is the committee. If there are no restrictions at all here, and we just have a certain number of people that we're pulling from, and it's like, so we have 3 people, and we can, like, how many, and there's no restrictions, like how many ways are there pulling 3 from 3 people, 2 from 3 people, 1 from 3 people, 0 from 3 people. Then we get a very nice committee, 1 plus x cubed. Similarly, committee B is just or 1 plus x or x plus 1, doesn't matter. The same thing to the fourth. So if we put these together, we just get 1x, 1 plus x to the 7th, and we're just looking for the coefficient of x to the 5th. Well, that's just a binomial coefficient computation, and we're done, 21. So that's a nice kind of committee problem when there's no restrictions at all. Then we can just use binomial coefficient magic and get it. All right, let's look at another idea. So how many different ways are there of putting n things into n boxes? Well, isn't that a multinomial coefficient problem? So because we have, like, think about this, we have like n different variables going on. And why is that? Because each committee is like the sum, and maybe we should write this out here. Let's go ahead and write this out. So each committee, like n different things. Let's label our variables like this: x1, x2, and dot 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 plus xn. And each committee will look like this. And these variables are distinct. They're different variables. I'm just labeling them so I can have n different variables. Now it's kind of like this committee or this factor is like an object, and we're either going to throw it into the x1 bucket, the x2 bucket, or the x, so all the way over, all the other variables are buckets. We could go into any of them and then up to xn. So it's like saying, okay, so but we're going to have n of these guys multiplied together, right? And so, and each one of these can either go to here to here. That's the same thing as saying, from when we multiply it out, we can either pick this or this or this or this or this to come from it when we multiply it out. It's like saying this object can go to any one of those buckets. So it's like we're multiplying this raised to the nth power out, and we're looking at, what are we looking at? Looking at a particular coefficient, right? What coefficient are we looking for? We're looking for the coefficient that looks like of x1, where we have one thing in this box, one thing in that box, to the first power, one thing in that box, and so forth. So basically, it's just the product of them all through x to the n. So we're just looking for this coefficient. So we're looking for that coefficient. How do we do this with the multinomial computation? We remember that it's just n factorial divided by 1 factorial, because that's all those exponents right there. So just the product of lots of ones. So it's just n factorial. So n factorial is another way. You can get that from a multinomial coefficient. It's kind of interesting connection. But what is n factorial? It's the number of ways of putting n things, arranging n things in n boxes. That's the same thing as how many different ways are there of arranging n things, or how many permutations are there of n things, n factorial. How many ways are there rearranging this, right, of x1? Because you can think about each one of these objects as being like a move, right? So you have a move, and this move is either going to be an x1 move, x2 move, x3, right? But it just can be one of them, right? And so in this process, base per move, it's like you have 10 different positions, and what's going to go in each position, and the way to compute that, just like the move idea that we had, is with this multinomial coefficient. So we actually end up getting n factorial as being the number of ways of rearranging n different things. Okay, so kind of a neat connection there. All right, so let's look at this this example right here, example 7. All right, this has to do with proving an identity between binomial coefficients using polynomial multiplication. All right, so maybe we have an identity like this. All right, so this plus this is always that, no matter what n and k are. Well, I mean, k less than n, perhaps, so it makes sense in our context that we're working with. And positive and integers and so forth. Well, yeah, how can we do that? Like, how can we show this? So we know that we're supposed to use polynomial multiplication to show this. Just think about what these things are. These are coefficients. When do coefficients add? That's when you're adding like terms. Oh, like terms. So maybe the result of a multiplication where you get where these are like the coefficients of some like terms. What is this the coefficient of? Hey, we know some things about binomial coefficients, what they're the coefficients of. Like, what is this the coefficient of? Right here, the coefficient of x, it's the coefficient of x to the k when we're writing out x plus 1 to the n plus 1. Now, what is this? This is the coefficient of x to the k and x plus 1 to the nth. What is this? The coefficient of x to k minus 1, because if k minus 1 here, if k there, okay, and x plus 1 to the end. So that's helpful. So we're kind of talking about a way we can work backwards to get what the polynomials are, and then actually see that it really is right and really does work. Okay, so let's take a look at how we would do this. Notice, okay, the coefficient of x to the k minus 1 in here. Okay, so it's like this times x to the k minus 1. But since we're adding, notice that this power is different than that power. So that's why I have a times x here to make up the difference. So let's just multiply x to make sure that, but kind of keep this going on. And then we have x to the k, and that's equal to, that's good. So we have like terms. But why in the world do we have so this times x? That kind of tells us something. This tells us that we have, that we've multiplied something, and notice how we have an n here and n here. So both of these guys are actually coming from the same place, x plus 1 to the n. And now also notice, so, but then we have an x coming in and a 1 coming in times. So 1 times x times. It's almost as if we have something like this. So we have lots of coefficients in here, and one of them we're taking with a 1 multiplied to it, one of them we're taking to the x multiplied to it, but in such a way that we have an x to the k power. In fact, there's only 2 ways of getting that, because the 1, how does the 1 get an x to the k power? By multiplying to an x to the k power. How does an x get to an x to the k power? By multiplying to an x to the k minus 1. In fact, this is exactly what we get. X plus 1 times x plus 1 to the n, and hey, that's x plus 1 to the n plus 1. And that's exactly what we have here, this coefficient. So we're really just equating coefficients in this multiplication, and that's it. So to prove this, all we state is we have this multiplication, and then what we do is we say when we multiply this into this, all right, this is going to have lots of coefficients. Binomial coefficients are going to look like this. And the 2 terms that will actually give an x to the k will be the ones that have, when we're multiplying by x plus 1, would be this one, and then this one, and when we multiply it by x. And then this will be the x to the k term over here. The x to the k term over here is that. So based off of that and equating like terms, we're done. We've actually shown the equality because we're just adding the coefficients up. Okay, in fact, I think this works through that process a little bit further. Okay, and kind of discusses it, but that's basically what we have. Okay, so here's another idea. Notice in the last example, we were multiplying by x plus 1. We can label that as or 1 plus x. We could do 1, 1 here. Think of this tabular multiplication. Now, when we multiply, with this shifting mechanism going this way, and let's not truncate it. Let's just keep it going. And we add down. Notice it's kind of like we have 1 and 3, 3, 1. Notice what we've done. We've kind of, this 2 plus 1 is like 2 plus 1 here, because this one's like that one. This 1 plus 2 is kind of like 1 plus 2 going that way. So it's kind of like we've taken 1, 2, and 1. We've added what's adjacent to get that, what's adjacent to get that, and then we put 1s on the ends. In fact, we can continue this process through, and to get the next line of this triangle, if we were to kind of think about this, what is this? What was this? This was taking this polynomial x squared plus 2x plus 1, and we multiplied it by x plus 1. And doing so, we got this. And how did the coefficients, at least? And how did we get that? We get that by just adding adjacent things. So what if we take this next line and we multiply it by x plus 1 again, and then we should get, and then the next line right here should actually refer to x plus 1 to the 4th. How would we get that? Well, we just do the same thing. We add those two to get 4. Here we get 6 when we add. Here we end up getting 4. and then we have a 1 on the end and a 1 on the end. We should get this, and this is exactly what we get. So this is called Pascal's triangle. It's a quick way to get binomial coefficients, at least if they're not too big. It gets very long if we go too far down. But this is just another viewpoint and way of looking um, at looking at how to get binomial coefficients. Okay, so and then we will end this video right here. Thank you so much for watching.